Have you ever wondered just how many kinds of arrows there are in organic chemistry? Well, stay tuned, because I bet it's more than you think. Hey there, OChemNinjas. I wanted to make a video where I walked through all the different kinds of arrows in organic chemistry. So I went looking around, gathering up the different examples of kinds of arrows. I thought there would be maybe 5 or 6, maybe 7 different kinds of arrows. Boy, was I wrong. By the time I finished my list, I had 15 different kinds of arrows that are used in organic chemistry. And I'd like to show them to you today in one comprehensive list. We'll start with the most common and most important kinds of arrows, and we'll finish with ones that you probably won't see all that often. The first is the humble reaction arrow. This workhorse arrow you see in almost every reaction scheme. It provides the frame for the starting material, the reagents, and the solvents to form a particular product. Given a starting material or a substrate, it tells us what reagents, catalysts, or solvents are needed to turn this starting material into the provided products. We probably take this kind of arrow for granted. I think we pretty much all understand what this arrow means. But there are some nuances with this arrow that I bet you weren't expecting. You can use this arrow multiple times to show multiple steps in a reaction sequence. The number of arrows doesn't necessarily equate to the number of reactions needed. By convention, we pretty much just use 3 arrows. The multiple arrows indicate that this starting material can't be turned directly into the product in one step, but it can be transformed into the product through a series of unnamed steps. When you see this arrow, it's intended to say that, yeah, we're doing some stuff to turn the starting material into this product. That's not important. What I want to highlight is that I'm turning the starting material into this product. We can also view a sequence of steps on one arrow if we delineate those steps with numbers. I'm going to get on a soapbox here a little bit. As far as I know, there's no formal convention for how to use these numbers, and it drives me a little bit crazy. Sometimes chemists will use these numbers to delineate different individual reaction steps in a sequence. But sometimes they will use these numbers to indicate different parts of one reaction. And I wish those were not used interchangeably. The convention that I use, and the convention that I wish all chemists would use, is that each different ordinal number would represent a completely different reaction. Think about it like weeks in your organic chemistry laboratory course. For step number 1, you would come into lab, you would do the reaction, you'd mix the reagents, you'd do the workup, the extraction, the crystallization, whatever you needed, and you would get a product at the end of step 1. Then in week 2, you would come in and do a completely different reaction. You could take the product from week 1, add new reagents, do a reflux, maybe a distillation, and you would get a new product at the end of week 2, at the end of step 2. Step 3 would be a 3rd week in lab, and step 4 would be a 4th week in lab. Different, complete reactions. Contrast that with this hydroboration. Using the lowercase Roman numerals here indicates that these are different parts of the same reaction. Everything here is occurring within the same week in lab. We come into lab, we start with the starting material, we add borane and THF, and we let that react for a while. Sometime later, we add sodium hydroxide and hydrogen peroxide, and then we do our workup, our extraction, our column chromatography, and we finally get our desired product. That's all one reaction, 1 week in lab. Sadly, I see chemists use these ordinal numbers when they're really trying to denote different parts of the same reaction, and I just think that gets confusing for students. The way I like to do it is to use the keyword then. We start with borane and THF, then sometime later, we add the hydroxide and the peroxide. To me, this is clear that this is all part of one transformation, 1 day in lab. Then I could have a step 2, and step 2 might be something completely different that I would do a different week in lab. I'm getting a bit off track. These don't have so much to do with arrows, but these are ways we can use the humble reaction arrow in organic chemistry. Another variation on the reaction arrow is the reversible or equilibrium arrow. The equilibrium arrow shows that this process is happening both in the forward and the backward direction at equal rates. The equilibrium arrow can be biased to show that either the products are favored or the reactants are favored at equilibrium. I want to contrast the equilibrium arrows with the reversible process arrows. Notice the double-headed arrow in the reversible process and the single-barbed arrows in the equilibrium. The reversible process arrow says that we can do a reaction in the forward or the backward direction depending on the conditions. The formation of an ester from a carboxylic acid is a reversible process. We can add an alcohol and an acid to form an ester, or we can start with the ester and we can add water and an acid to turn it back into the carboxylic acid. That process is reversible. Tautomerization, on the other hand, is in equilibrium. At equilibrium, these two species are interchanging back and forth equally at the same rate. It's a subtle difference and one that might not be emphasized all the time, but it is a true difference in the arrow usage. We can also take that reaction arrow and make it a dashed arrow. The dashed arrow is where we show future reactions, reactions we haven't done yet but plan to do. If we are giving a scientific talk, we can say that we have completed the reaction, turning the alcohol into a ketone, and when we get back to lab next week, we're going to do the alkylation reaction. We can also use the dashed arrow to show unknown reaction conditions, such as if you were an ambitious chemist and wanted to make the molecule Taxol from dimethyl cyclohexene. It's unknown at this time what reagents you would actually need to pull off this transformation, so we would use the dashed arrow. Eventually, I think it would turn into our next kind of arrow. The broken arrow shows reaction conditions that just didn't work. The arrow can be broken with an X or with the parallel lines, but it shows that under these reaction conditions, these starting materials were not in fact turned into those products. You can't do an SN2 reaction on a tertiary alkyl halide. You can't randomly deprotonate an alkane with sodium hydroxide and add on an alkyl group. Our next arrow moves us out of reaction arrow land and shows us the resonance arrow. The resonance arrow separates individual resonance contributors in a resonance series. By putting arrows on both sides, it shows us that these molecules only differ in their placement of lone pairs and pi bonds. Notice the difference between the resonance arrow and the equilibrium or reversible process arrows. The resonance arrow cannot be used interchangeably with the equilibrium arrows. Let me also take this time to remind you that the individual molecules within a resonance series do not actually exist. None of the individual contributors in a resonance series actually exist. The only thing that exists is the resonance hybrid. And now we get to my favorite arrow as an organic chemist. Curved arrow is probably the most important arrow in organic chemistry. The curved arrow is our main storytelling device in organic chemistry. The curved arrow shows the movement of two electrons as they move from a place of high electron density to a place of low electron density. That can either be in the form of resonance contributors or in the form of a reaction. The curved arrows tell a story. They tell the story of the movement of electrons. They tell the story of old bonds being broken and new bonds being formed. Only electrons move in organic chemistry, and the curved arrow shows how they move. For this resonance series, this arrow says that we are taking the electrons that used to be shared in a pi bond between carbons 3 and 4, and we're moving those electrons over to form a new pi bond between carbons 2 and 3. As a result, we're taking electrons away from carbon 4, so carbon 4 will have the new positive charge in our new resonance contributor. Notice there's no curved arrow showing the movement of the positive charge. Charges don't move, only electrons move. Charges change places as a result of electrons moving. Here, the arrows tell a story as well. We're taking a lone pair of electrons that used to be localized on oxygen, and now we're sharing them with the hydrogen atom to form a new oxygen-hydrogen bond. Hydrogen only makes one bond, so we need a second arrow to show that the hydrogen-chlorine bond is breaking. Those electrons that used to be shared between hydrogen and chlorine are now moving on to chlorine as a new lone pair. The curved arrow is also the blueprint that tells us how to draw the products of a reaction. This first arrow depicts a bond-forming event between oxygen and hydrogen. We need a new oxygen-hydrogen bond in our product. The second arrow depicts a bond-breaking event. We're breaking the hydrogen-chlorine bond, so chlorine is off on its own as a leaving group on the product. A variation of the curved arrow is the fishhook arrow. The single-barbed fishhook arrow shows the movement of one electron rather than a pair of electrons. These are used exclusively in radical reactions. We can use fishhook arrows in radical resonance to show how one resonance contributor is converted into a different resonance contributor. We are taking the pi bond between carbons 3 and 4 and forming a new pi bond between carbons 2 and 3. I need 2 electrons for that bond. I can get 1 electron from the radical and 1 electron from half of the pi bond, and those 2 electrons will come together to form the new pi bond between 2 and 3. I need to show the movement of all electrons, so when I break that pi bond, that last electron in the pi bond is going to get deposited on carbon 4 as a new radical. We can also see radical arrows in the 3 types of radical reactions that can occur. We use the fishhook arrow in homolytic bond cleavage. The bromine-bromine bond breaks, and the homolytic bond cleavage says that each bromine gets 1 electron equally. This forms 2 bromine radicals. We also see it with an alkene addition. I want to form a bond between the bromine radical and the carbon number 4. I need 2 electrons for that bond. I can get 1 electron from the bromine radical and the other electron from half of the pi bond. When I break the pi bond, I need to account for both electrons, so the other pi bond electron goes on to carbon 3 as a new radical. We also use the fishhook arrows in combination reactions. 2 individual bromine atoms come together to form a bond. I need 2 electrons for that bond. I get 1 electron from one bromine, 1 electron from the other bromine to form the bromine-bromine bond. And that concludes the tier 1 level of arrows in organic chemistry. From here on out, we're kind of in tier 2 territory. Still important arrows, but we won't see them quite as often as the other arrows. The retrosynthetic arrow is a very important arrow in organic synthesis. The retrosynthetic arrow allows us to think backwards in organic chemistry, where the product is on the left side of the arrow and the starting materials are on the right side of the arrow. This is not intended to be a real reaction, it's more intended to be a thought experiment. The retrosynthetic arrow with the 2 stems on that arrow means something very specific. It means that this product was made from these starting materials. Let me be very clear. It is not saying that we are turning this alcohol into an aldehyde and a Grignard reagent. That is not what we're saying. In fact, it's exactly the opposite. We can use this aldehyde and Grignard to come together to make this alcohol. The retrosynthetic arrow allows us to think in the backward direction. This alcohol was made from these reagents. The dipole arrow helps us illustrate important properties of organic molecules. When we have a covalent bond between 2 atoms of differing electronegativities, that bond is a polar covalent bond. Most of the electrons will be around the more electronegative element in that covalent bond, and there will be fewer electron density around the less electronegative element. And the dipole arrow illustrates this. The dipole arrow is an arrow with a cross through the stem, and that cross through the stem is meant to illustrate a plus sign. This is a positively charged side of this arrow. It's indicating that this carbon is electron deficient with a partial positive charge, and that most of the electron density is around the more electronegative bromine atom. We can also use the dipole arrow to show the entire molecule's dipole moment. The entire dichloropropane molecule is a polar molecule. For the entire electron cloud around this molecule, it is mostly pulled around the 2 chlorine atoms as the more electronegative elements in this molecule. For the molecule as a whole, there's more electron density around the chlorine parts and less electron density around the rest of the molecule. One of my favorite arrows to draw is the photon arrow, the little squiggly line with an arrow at the end. The photon arrow indicates that there's a photon of light interacting with our chemistry somehow. Many radical reactions require a photon of energy in order to initiate the reaction. When a high-energy photon hits a molecule of bromine, it can homolytically cleave that bromine-bromine bond, forming the two bromine radicals and starting the radical reaction. We can also see the photon arrow in a molecular orbital diagram. When a molecule is irradiated with a photon of sufficient energy, it can excite an electron up to a higher energy level. This can only occur if the energy of the incident photon exactly matches the energy of the energy gap between the two orbitals. There is a discrete energy gap between these two orbitals that corresponds to a certain amount of energy. The photon hitting that molecule has to be exactly that same amount of energy or nothing happens. We can also use the photon arrow to show that a photon of light is emitted in a chemiluminescent reaction. A chemiluminescent process is a chemical reaction that releases photons of light. When luminol is treated with hydrogen peroxide, it glows and it emits photons, and we can use the photon arrow to show that it is emitting those photons. When a reaction evolves a gas or causes a precipitate to form, we can use the precipitate or gas arrow to show the evolution of the gas or the forming of the precipitate. When calcium bicarbonate and calcium hydroxide react, they form calcium carbonate, which precipitates out of the reaction as a solid. The down arrow denotes that the product is precipitating out. When elemental magnesium reacts with hydrochloric acid, it forms lots of tiny little bubbles of hydrogen gas, and those hydrogen gas molecules evolve out of the system, and we use the up arrow to show the evolution of that gas. When we draw molecular orbital diagrams, we can draw the picture of all of our orbitals. Orbitals exist, then we can put electrons into them. After we've drawn the orbital picture, we can add electrons to that molecular orbital picture using Hund's rule and Aufbau principle and Pauli exclusion principle, and the arrows that we use are the orbital electron arrows to fill those orbitals. An arrow that we really don't see all that often in organic chemistry is the coordinate covalent bond arrow, or sometimes called the dative bond arrow. We typically think of a covalent bond as the sharing of electrons between two elements where each element contributes an electron to that covalent bond. A dative bond or a coordinate covalent bond indicates that all of the electrons in that covalent bond, both of those electrons are coming from one of the atoms in that pair. When copper 2+ is hydrated, the 6 oxygen atoms of the 6 water molecules contribute all of the electrons towards that bond with copper. In N-methylmorpholine and oxide, the nitrogen-oxygen bond, nitrogen contributes both of the electrons to that bond, so we could use the dative bond to show that. We can use arrows to show that we are manipulating or rotating or translating molecules in three-dimensional space. We can use an arrow to show that we are changing our perspective as a chemist to look at the molecule from one side or the other. We can use a little curlicue arrow to show that we have done some kind of manipulation. We haven't changed the molecule, we've just changed our perspective of the molecule. We can use that curlicue arrow to show chair flips and chair conformations. And we can use it to show 120 and 180 degree bond rotations about a single bond in a molecule. We can use this arrow to show that we are rotating this particular bond to get to this new conformation of the molecule. The last arrow that I'd like to show you today is one we really don't see all that often, but when you do, now you'll know what it is. And it is reflux arrows. We use this up-down arrow pair underneath the reaction arrow as a set of reaction conditions to show that this reaction is being refluxed. This reaction must have some kind of high activation energy barrier. We need to input energy into the system, and we're doing so in the form of heat by refluxing the reaction. The reaction is being run in ethanol, and we are boiling that ethanol to add energy into the system. The ethanol will vaporize and condense in a condenser and drip back down into the flask. That way we can elevate the temperature without losing solvent along the way. Which arrow is historically confusing for you? Which arrow do you always have to stop and think, what does this arrow mean again? Leave me a comment below and maybe I'll make a full video about it. Thanks for watching. If you like what you saw today, maybe let your instructor know about these videos, or your friends at other schools. Check out some of these other videos and playlists, see what you like. As always, don't forget to like and subscribe.